All right, ladies and gentlemen, we're going with the Unit 3 review today. All right, so let's talk about these things. Thompson's model. Well, first of all, he said it looked like a plum pudding or a cookie. I don't care. Sketch looks like this. It's got some random positive charges, and it's got some localized negative charges. And the merits. He got the size to charge, or mass to charge ratio, sorry. Let's do that. It is a size, but mass to charge ratio of the electron. He basically told us how big he thought the electron was. And that's about it for the merits. The limitations, well, he didn't know where any of the particles were located. Yeah, so really all Thompson could tell us is that there were positive and negative charges. Fantastic. And I guess I should put plus charges. But he couldn't tell us where anything was, right? All right, and then Rutherford came along and he did the gold foil experiment. And what he figured out is that there was a dense, positively charged nucleus. And that's about it. And the limitations, he didn't tell us anything about electrons. And then Bohr came along, and Bohr gave us Bohr structures, merits. He identified electrons in shells, and I'm going to put parentheses energy levels. And limitations, couldn't narrow down location of electrons. And then we had our current view, which is based on probability. Merits, exact locations of electrons. Yeah. And we don't know the limitations of our own model yet right now. What contributions did Thompson, Rutherford, and Bohr make to the development of modern atomic theory? Well, I mean, I just said it, right? They gave us their models, right? And so I gave you the merits of their models, so I don't feel like rehashing the contributions of Thompson, Rutherford, and Bohr. I will tell you that Bohr made one more contribution beside identifying the shells and energy levels, and that's that electrons can go from the ground state to an excited state, and that when it falls back down again to the ground state, it emits a photon of light. And that's about all we need to know as far as contributions or other contributions beyond, what I've shown you up here in this chart. Just simply knowing that Bohr did this as well. Okay, complete the following table about subatomic particles. All right, so the symbol for proton, P+, the charge, plus relative mass, 1 AMU, location, nucleus, and determines identity of the element. And then we have an electron, which is E minus. Its charge is negative. Its relative mass is 0. Its location is in clouds around the nucleus, surrounding the nucleus. I mean, or in shells around the nucleus, however you want to say it. Electrons determine ions, right? If I lose one electron, I become an anion, like all the things here do. So that's what electrons do. Neutrons, it is N naught. It is 0 charge.
Students, if you're not with a teacher, coach, or club sponsor, it is time to leave campus or report to the Gold Gym lobby to wait for your ride. Once again, students, if you're not with a teacher, coach, or club sponsor, it is time to leave campus or report to the Gold Gym lobby to wait for your ride.
Neutrons have no charge, but they weigh 1 AMU. Remember, neutrons and protons weigh, but only electrons and protons have a charge located in the atom and the nucleus. Seems like a natural place for a neutron to hang out. And it determines the isotope. That's all that changes is the number of neutrons in an isotope. All right, page 1 in the books. Page 2. Why do we use the atomic number to identify an element and not the other subatomic particles? Because protons identify the element, not neutrons or electrons. And the atomic number gives us the number of protons. That's why. The atomic number, oh wait a minute, let's use something here that's not as shiny. 15 for phosphorus. That tells us how many protons. It never changes. We never can change the number of protons. So that's why we use the atomic number to identify the element, because neutrons change in number and so do electrons. These things tend to gain an electron, so therefore they're going to have the same number of electrons as the thing right beside them, right? Okay. Define atomic number and mass number. All right. Atomic number is number of protons in element. Mass number is protons plus neutrons. What do these two numbers tell you about an element? What do they tell you about isotopes? Well, in an element, they tell me how many protons I have, and a mass number, if I subtract out the atomic number, tells me about the number of neutrons. And what do they tell you about isotopes? They give me the number of neutrons in a given isotope. As in, so carbon 12, if I have carbon 12, I subtract out 6 protons, I get 6 neutrons. Carbon 13, if I have the mass number and I subtract out the number of protons, which is 6, then I get 7 neutrons. So it just tells me the number of neutrons in a given isotope. What is an ion? It is a charged atom. An atom with a charge. Explain how are they formed and state the difference between cations and anions. They are formed by gaining or losing electrons. Cations lose electrons and are positively charged. I'm just going to put positively charged. Anions gain electrons and are negatively charged. Yeah, so an ion is any atom that gains or loses electrons. So like we said with fluorine, fluorine has 7 valence electrons, so it has a tendency to gain 1. If I gain 1 electron, I become an anion, a negatively charged anion. Things on the left side of the periodic table tend to lose electrons. This alkali metals here, they have 1 valence electron, so they tend to lose that rather than to try and gain 7. If I lose an electron, I am positively charged and I am a cation, so all things here are cations, all things here are cations, all things here, here are anions, and these things are not charged at all. These are noble gases, right? 0 charge. Okay. All right, identify the parts of the isotopic notation. How many neutrons are in this element? Okay, so the top number is the mass number. That is protons plus neutrons. The bottom number is the atomic number, which is also the number of protons. So if I subtract the number of protons from protons plus neutrons, then I have just neutrons. So this thing has 12 neutrons. Therefore, it is sodium 23. That's how I would isotopic name for it, right? So sodium 23 would be its name. It has 12 neutrons because 11 from 23 is 12. Okay? Okay. Let's see if we can get some of this chart done. All right, so they give me the mass number and the atomic number, so this is going to be pretty easy, right? The atomic number is the number of protons, is the number of electrons. A equals P equals E. A, P, E. So I'm going to go through and do all those first. So 3, 3, 3, 35, 35, 35, 92, 92, 92. And then we're going to go back and add the isotopic symbol. So argon is Ar, and remember it's the mass number up top and the atomic number on bottom. Lithium, Li, mass number up top, atomic number down bottom. Bromine, Br, mass number up top, atomic number on bottom. Uranium, mass number up top, atomic number on bottom, right? Yes. Okay, so we got 38, let's see, that's 140, what? 140, oh my God, I'm gonna need a calculator. Y'all's bad math is rubbing off on my brain. No, I can't do math without a calculator either. 238 minus 92 equals 146. And then 85, so let's see, that'd be 45. 3 from 7 is 4 neutrons, and 18 from 40 is 22 neutrons. All I'm doing is subtracting the atomic number from the mass number to get the number of neutrons. Atomic number from mass number. Okay, so that's the first part of the table. Let's call that video number 1, and then I'll start with video number 2 right